Hello, I'm Jim Salisbury with Metrology America Corporation, and welcome to the Metrology Training Lab. In this episode, we're going to talk about some quality rules that are often used in calibration to determine the acceptability of measurement standards or systems. For example, in a past episode of the Metrology Training Lab, we discussed the calibration of micrometers and recommended grade 0 gauge blocks, saying that they were sufficiently accurate. Well, what do we mean by sufficiently accurate? What calculations can you make to justify the selection of measurement standards or your calibration providers based on quality? In this business, many organizations make decisions based on ratios between the accuracy of what you are checking and the accuracy of what you are using to check it. We're going to discuss two of these common ratios, one being called the test accuracy ratio, or TAR, and the other being the test uncertainty ratio, or TUR. These are sometimes called the TAR and the TUR. Let's start with the TAR, and we'll use the micrometer calibration as our example. For a typical 0 to 1 inch digital micrometer, the accuracy specification for the mic is plus or minus 50 millionths of an inch. We want to calculate the TAR at 1 inch for the example where we're using grade 0 gauge blocks in the calibration of this mic. So we need to know the accuracy of the gauge blocks. The tolerances for the grades of gauge blocks are defined in the American National Standard ASME B89.1.9, but are available from many sources, including the Metrology catalog. I can look up this and see that the length tolerance for this 1 inch grade 0 gauge block at any point on the gauge block is plus or minus 6 millionths of an inch. The TAR is defined as the ratio of the accuracy of what you are checking to the accuracy of your measurement standards. So that would be the accuracy of what we are checking, plus or minus 50 micro inches for the micrometer, divided by the standard that we're using, the gauge blocks, the plus or minus 6 micro inches. If I do this math, I'll find out that my TAR is about 8.3. This means that the gauge blocks are over 8 times more accurate than the micrometer being calibrated. So is a TAR around 8 good enough? This is the first question in this episode that I cannot and will not answer. I can teach you how to calculate the TAR, but I cannot tell you what level of risk is acceptable for your organization. I can't even tell you if calculating a TAR is the right thing for you to do. I can tell you, however, that there are a number of organizations that require TAR calculations for calibration work, and that the most common rule is the so-called 4 to 1 rule, or a TAR greater than 4. The TAR rule has been around formally since at least 1950, when Military Standard 120 was published. But the rule then was a TAR of 10, or 5 in certain cases. Maybe you have heard of the so-called 10% gauge makers rule. That's a TAR of 10, and some organizations still use the 10 to 1 rule. I gotta tell you the truth. There is a limit to the usefulness of TAR calculations. Many organizations these days, in particular accredited calibration labs like ours here at Metrology America, do not use TAR. Instead, we use the TUR. So what is that? Let's look at our micrometer calibration again. We are calibrating the micrometer with these gauge blocks. The TAR looks at the relationship between the gauge blocks and the micrometer. But there are other things than just the gauge blocks that are affecting the quality of this measurement. One big source of variation in dimensional measurements is the impact of temperature, and the TAR calculation does not consider that. The standard reference temperature for length is 68 degrees Fahrenheit or 20 degrees C. This means, in theory, that all measurements should be made at exactly 68 degrees Fahrenheit. Of course, that's never possible, and we try to get as close to 68 degrees Fahrenheit as we can afford to. And just like the imperfections of these gauge blocks and their calibrations can cause errors, so too does our inability to achieve a perfect 68 degrees Fahrenheit. Both the calibration of this gauge block and the temperature of the lab environment creates errors. Or put a slightly different way, they can contribute to the uncertainty of the measurement. Now, I'm not going to attempt to turn this episode into a lesson on uncertainty. We don't have the time for that. However, I can demonstrate a TUR calculation. For the interested viewer, you can find an example uncertainty evaluation for a micrometer calibration using grade 0 gauge blocks in the American National Standard on Micrometers, ASME B89.1.13. The final analysis in that uncertainty was 10 millionths of an inch. Since that seems like a reasonable, achievable uncertainty, let's use that to calculate the TUR. Our micrometer tolerance is still the plus or minus 50 millionths. Our measurement uncertainty is the plus or minus 10 millionths. The TUR, similar to the TAR, the TUR is defined as the ratio of what you're checking, plus or minus 50, divided by the uncertainty, the plus or minus 10, which gives me a TUR equal to 5. Now, is a TUR of 5 good enough? What is an acceptable TUR? That, my friends, is a question that people have been fighting over for many years. Once again, I cannot tell you an answer because I cannot tell you what level of risk is acceptable for you. I can and will tell you, however, that the most common rule is a TAR or TUR of 4 or larger. And the default rule in many of the ASME B89 standards is a TUR of 4 or larger. And the reason we recommended grade 0 gauge blocks for the micrometer calibration is that you should likely be able to achieve a TUR of 4 or larger with them. Now, the reality is that achieving a TUR greater than 4 can be difficult or impossible at times. So you need to be careful, particularly when hiring calibration services. I've seen some organizations put a requirement in calibration purchase orders that the lab must disclose in advance of any calibration work if the TUR is less than 4. I think that's a pretty good idea and does a nice job of protecting you. I personally don't like seeing really low TURs. For example, TURs under 1. In those cases, it means the calibration capability is worse than the tolerance being checked. Let me say that again. The TUR is less than 1. It means the capability to do the calibration is worse than the equipment being checked. That just doesn't feel right. However, it happens. And the worst case I've ever seen, in my experience, is where the TUR was 0.1. In other words, the calibration was 10 times worse than the equipment being calibrated. Really? That's like giving a toddler a pair of scissors and asking them to give you a haircut. It's not going to turn out well. So that's all for this episode. I hope you've learned a few things about TAR and TUR. There's a lot of confusion in the calibration business on this topic. I'd be interested in hearing about your experiences, so please post some comments or some questions. Thank you. I'm Jim Salisbury, and I'll see you next time from the Metrology Training Lab.